We are now recording. And when you believe you've factored this completely, these next two problems, you can go ahead and post them in the chat. And I'll take a look at them.
How do we do the third one? Like the second part of it, the 4m parentheses a plus b?
Well, can you tell me what the common factor is between the two terms?
2.
Is there another common factor?
Oh, 2a plus b.
Yeah. So we can factor that whole thing out, the 2 and the polynomial factor a plus b.
Okay.
Yeah. Yeah, that looks good, Gladys, what I'm seeing in the chat. So I'm going to go ahead and jump in. If you're not finished working with these, continue working and just sort of passively listen to my narration as I run through these problems. So when I look at a problem like this one, I'm sort of going to look at each of the terms and remember the terms are the things that are separated by either the addition or subtraction sign. So that's a good way to identify how many terms you have. So we have two terms here. We sort of have the negative 4p to the third power q to the fourth power. And then we have this minus 2p squared q to the fifth power. So I go term factor by factor. I look at the numeric factors, see if they have a common factor. Then I look at the variable factors and then see what is in common there, what we can pull out. So if I was trying to identify what the GCF is here, well, the first term is negative. So by convention, I'm going to pull out a negative sign. And since these are both sort of negative numbers or negative terms, that means that when I factor this out and I've taken away their negative signs, then I should have some sort of positive signs for those two terms. Okay, and then 4 and 2 have a 2 in common, so that's their numeric factor. We have a p to the third power here and a p to the second power here. Now, one way you could think about this is I can take away, or I can sort of factor out 2 p's from here because we have 3 of them in total. But I can't take or factor out 3 p's from this one since there are only 2. So if you have a common variable factor, you want to take the number of p's that has the lower exponent. So p to the second power. Then if we look at the q's, the q to the fourth power is the one that we want to take. Okay, so we'll go ahead and write our GCF down, negative 2p to the second power q to the fourth power. And we need to multiply that by 2 terms so that we get the original expression back. So just focusing on the first term, we need to think about what is -2 times something to get us back to -4. Well, that has to be a +2. It looks like we need a p to the third power, so we need an extra p in here. And q to the fourth power is okay. So we're good there. The first term inside the parentheses is just 2p. Then we can say, okay, we need to multiply -2 times something to get the -2 back. Well, that needs to be a +1. For now, I'm not going to put the 1 down yet. And we'll take a look at what else we need. So we have p to the second power is what we need. We have a p to the second power, so that's not going to be a problem. But we need a q to the fifth power. So we need an extra q. So you might feel tempted to put 1q here, but 1q is the same thing as just q. So we don't have to put that 1 since 1 times q is just q. 1 times anything is just whatever that thing is. So if we run through that multiplication, just to double check, -2 times 2 gives us our -4. P to the second power times p gives us a p to the third power. And then we'll have our q to the fourth when we multiply that out. That takes care of the first term. Then our -2 times an understood 1 will give us the -2 back. P to the second power, again, times that understood 1 is just going to be p to the second power, so we're good there. And then p to the q to the fourth times an extra q will be q to the fifth power. So this looks good to me. Finally, if you look at these two terms, their GCF, it looks like they have a 2 in common. So that's nice. And they have this polynomial factor here of a plus b in common. So really our GCF is going to be this complex of 2 times this polynomial. And if we divide that out of the original polynomial, so let me sort of draw an arrow, then I need to say, okay, I'm writing the GCF 2 times a plus b. And I need to multiply that by something so that I get these 2 original terms back. Well, the first term is 2 and then times a plus b. So I need to multiply this guy by some value, some term that will return itself. Well, that has to be the number 1. And another way you could think of that is if we divided out the GCF. So I'm dividing by 2 times a plus b. Anything divided by itself will divide to give us 1. Same thing over here. If I divide out the 2 times the a plus b, well, the a plus b will cancel out here. And then 4 divided by 2 should give us our 2. And we have an m left over. So this should be plus 2m. Any questions about those? Okay. So that was our first technique for factoring polynomials. We're moving on to our method 2 for factoring polynomials. And this technique is called factoring by grouping. It's very similar to factoring out the GCF, or the greatest common factor, except you have to do it a couple more times. So in the last set of problems that we just worked, we only had 2 terms, but you can factor out the greatest common factor for a polynomial of any length. That is, you could have 2 or 3 or 4 or more terms. But with factoring by grouping, typically in this class, we're going to be using this on polynomials that have 4 terms. So that's one way to identify when you need to use factoring by grouping. So if you have a polynomial with 4 terms, that's what you need to be thinking about, factoring by grouping. So let me give you an example of what this might look like. So let me grab my handy dandy notebook. And grab an example. So if we're looking at this polynomial, mp squared plus 7m plus 3p squared plus 21. We want to identify or count the number of terms that we have, again, at the beginning of looking at any polynomial that we're trying to factor. Counting the number of terms will direct you to what technique you need to use. And it turns out that there are 4 terms here, right? They're separated by the addition signs. We have mp squared, 7m, 3p squared, and 21. Now, the first thing that you should always attempt on processing and factoring a polynomial is checking to see whether all of the terms have some common factor. So if we look at these 4 terms, the first 2 terms look like they have an m, a factor of m inside them. And the second 2 terms don't have an m, okay? The first and the third term look like they have a p in common, but the second and fourth term don't have a p. So it's already sort of getting a little bit complicated to keep track of what factors belong where. The second and fourth term, the third and fourth term have a factor of 3 in them, since 21 is divisible by 3. But it doesn't look like all 4 of them have some common factor. So there's this neat property of real numbers, and it works for polynomial expressions too, called the associative property. And the gist of the associative property is this. When it comes to just an expression with numbers, if I'm adding 4 numbers, like let's say 2 plus 5 plus 6 plus 13, I could add that all up. Let's see what I get. So 2 and 5, maybe I want to do 8 there, 13. That should be 26. Okay. So if I add them all just straight across, I get 26. But if I go ahead and say, what if I group these and throw some parentheses around the 2 and the 5 and the 6 and the 13? Do I still get 26?
Yes.
Cool. What if I had 2 plus 5 plus 6 plus 13, keeping in the same order? And what if I threw parentheses around the 5 and the 6, and then I added the 5 and the 6 first, and then I worked with the 2 and the 13 later? What should I get when I add up those numbers?
26 still.
Yeah, the result didn't change because I grouped them. So if I have a string of terms that I'm just adding or subtracting, I can group them in any way I see fit, and it does not change the problem. It does not change the result. So that's going to be true with polynomials as well, that if I look at this 4-term problem, I can group the terms together so that maybe I can say, okay, the first 2 terms might have a common factor, and maybe we can factor out from there, just like we did those previous problems. Then we can turn our attention to the second set of terms, factor out their greatest common factor. And once we've done that 2 rounds of factoring out the greatest common factor, maybe there's a little bit more we can do to completely factor that polynomial. And that's the gist of this factoring by grouping. We're going to group the first 2 terms together, then we're going to group the second 2 terms together, and then see if we can sort of divide and conquer. So for this first set of terms, it looks like they have an m in common. So why not just factor out that m? So we can write that as m times p squared plus 7, ignoring the second 2 terms for a second. Does that look like a good factorization? Does anybody have any questions or concerns about that part?
No.
Okay, and it should make sense because if we go ahead and run through that multiplication, m times p squared gives us our original term back, m times 7 gives us our 7m back, so we're good there. It's an equivalent statement. We can turn our attention now to the second set of terms, and these two terms, like I said before, it looked like they have a 3 in common, so let's factor out a positive 3. And if we do that, we should have a p squared here, and then 3 times what gives me 21? Well, that should be a positive 7. Does anybody have any problems factoring that second set of terms? Cool. So now if I turn my attention back to the original problem, we've processed it a little bit. Now we have a polynomial that looks like that third example that we worked on at the beginning of class. We have a term right here. We have a term right here. And it turns out that their greatest common factor is now p squared plus 7. So since this is now the GCF, we can do one more round of factoring out the GCF, factor out their common factor, which is p squared plus 7. And once we factor that out, we're multiplying it by something that we have left over that would give us our original two terms back. Well, that would be the leftover m and the leftover 3. So now it turns out that this polynomial times this polynomial is the factored form of our original statement of 4 terms. So this is the final or fully factored form of our original problem. Does anybody have any questions there?
Is there a way to check your work on this method? Because I know there is with the method we just went over, but like with that last answer.
So to check any factorization, you multiply it out. So if I have this as my factorization, and I think that that is the correct answer, well, I can go ahead and multiply or FOIL p squared times m gives me mp squared times 3 gives me 3p squared. 7 times m gives me a 7m, and 7 times 3 gives me 21. So if I look at these 4 terms, are these the 4 terms that I started out with? Yeah. Well, I have my mp squared, I got my 7m, I got my 3p squared, and I got my 21. So this factored form checks out. We did it correctly. It might not be in the exact same order, but that's okay because there's another property of real numbers called the commutative property. And this one should be pretty intuitive to you guys, even though you might not have heard this terminology. It's simply the idea that if we have terms that we're adding together, like 5 plus 3, we know that that's 8. If I change the order of that addition, though, 3 plus 5, it doesn't change the result. So even with polynomials, if you rearrange the terms, the result's not going to change. So this is equivalent to what we started out with, which means that this factorization is correct. Okay, we're going to do a couple more examples. Let's see. Practice. Well, I'll let you guys work on a couple. 2y squared plus az minus 2z minus ay squared. X to the third plus 2x squared minus 2x minus 1. Okay, so take a moment, maybe 5 minutes, to sort of use what we applied in the last problem to try to factor these two polynomials by grouping. And again, once you have a factorization for your polynomial, you can go ahead and throw that in the chat or throw a thumbs up emoji in the chat.
Just to be clear, like we can group them in any order, right? It doesn't just have to be the first two and the last two.
I would say that you always try the first and last two, but I assume that you're asking me this question because looking at the first one, the first two terms don't have anything in common.
Yeah.
Yeah. So great question. You definitely can rearrange them. Again, by the commutative property, we can rearrange these into whatever order we see fit. Just be careful with the signs, right? If it's a negative and you move it to the front, then that should remain a negative. And then this guy should remain a positive since it's a positive. But my tip here is that if you don't automatically see them where the first two terms have something in common, I would switch the second and the fourth term. For some reason, in my experience, this seems to work out tremendously. So I would rearrange this first one to 2y squared minus ay squared, and then write negative 2z plus az, and then try that out.
Okay, thank you.
That's my pro tip. Does anybody else have a question, or is anybody just completely stuck?
I'm stuck like on the last part now.
Yeah, where are you stuck?
So I broke it down into like the second line that you have right there, and I got the second part. I don't get it. What happened?
Oh, for the last part.
Yeah, like the negative 2z plus az. If you take a z out, like the insides of the, so it would be what? Negative 2 plus a, but that doesn't match the other one.
Let's see. Yeah, I'll just go ahead and jump in here. We factor out a y squared, leaving us with 2 minus a. Then for these, oh, no, it's fine. Yeah. So remember when the first term here, since we're grouping these like so. I'm going to put a little plus sign here. The first term here is negative. So we need to factor out the negative GCF. Okay, so we're going to factor out a negative z since they have a z in common. But if we do that and we want to multiply that negative z back in to get our original statement, well, we already have the negative sign here. So we only have to multiply this by a 2 to get this original term back. Similarly, we have a negative number here that we need to multiply by something to get a positive. So that has to be a negative, since a negative times a negative gives you a positive. And the only thing that we're missing is our a. So it turns out that the stuff that's in parentheses are a common factor between these two terms now is R2 minus A. So it's the exact same. And you're absolutely right to have stopped there if you didn't match those. They have to match in order for you to proceed. If they didn't match, then you made some mistake when you factored out the first round of GCFs.
Oh, okay.
Yeah. So that's a good like tip to sort of self-regulate while you're going through the problem, right? If those factors in the end in parentheses don't match, then you're not going to be able to factor them because they're not a common factor. So some other mistake must have gotten you to that place. So when that happens, I would just start at the top to see where did the mistake happen? As opposed to like searching for the mistake, just start fresh. Because starting fresh, it always saves you time as opposed to looking for, a sign error somewhere. It's harder to see. So we'll factor out our 2 minus A, that's our GCF, and then we're left with our y squared minus z, and that's the complete factorization. I'll leave the checking to you guys at that point because you can multiply those terms out, those polynomials, and you should be able to get the full polynomial, the 4 terms that we started with. Does anybody have any other questions about the first one? It looks like some people have finished the second one as well. So we can jump right into that. This is really nice, actually, I think, because I think it's already ordered in a way that will work for us. So I'm just going to throw parentheses around the first 2 terms and the second 2 terms. I'm going to put a plus sign here. The reason why I'm throwing the plus sign here is because if I just simply throw parentheses on the problem and I didn't put the plus sign in the middle, it would look like I'm multiplying 2 polynomials. But the original expression was simply the addition and subtraction of a bunch of polynomial terms. So it's not the same if I just throw the parentheses on, because then I'm sort of changing the problem to a multiplication problem, which it never was. So I put the plus sign in there just to ensure that it's clear that I was adding a bunch of terms together. Okay, that's sort of a very, maybe it's an esoteric thing, maybe it's me being a little bit of a stickler, but it's mathematically correct. In any case, we're going to treat this the way we treated the last problem. The first 2 terms, what is their greatest common factor?
2x squared.
Yeah, 2x squared. So I can write that down and open up some parentheses. Then ask myself, what do I need to multiply to get these original 2 terms back? So 2x squared times another 2x should give me my 4x to the 3rd power. And then something times times 1 will return itself. So we need a plus 1 here. Is everybody okay with that?
Yes.
Okay, so now the second 2 terms are both negative. So I need to factor out the negative GCF, but it sort of doesn't look like there's anything in common. Well, here's the tricky thing. Every number has a factor of 1 inside them, right? Like 3 can be written as 3 times 1. 2 can be written as 2 times 1. Even 1 can be written as 1 times 1. So if it doesn't look like there's anything we can factor out, except for this negative sign, well, then let's factor out a negative 1 and see how that changes the polynomial. So negative 1 times something to give us this negative 2x back has to be a positive 2x. And then negative 1 times positive 1 should give us itself back, so positive 1. And again, the reason why this is positive is because if we had put a negative 1 here, a negative times a negative would make this a positive, and that wouldn't be correct. Okay, so we've done the tricky business of factoring out a factor of 1, But that trick is actually pretty neat because now the stuff in parentheses matches exactly. So we can say that among these two terms, that the stuff in parentheses, the 2x plus 1, that polynomial factor, is the greatest common factor that we can now factor to the front. We get 2x plus 1. And then what our remaining factor will be is the 2x squared minus 1. And that's the fully factored form of our original expression. Any questions there?
So you got at the beginning, so when you to get that 2x squared there, what is that? Just like the common denominator between 4 and 2 is how you did that?
2x squared.
It's
It's the common factor between these first two terms.
Two. Okay.
Yeah, because they both have a factor of 2 inside them.
Mm-hmm.
And then if we're looking at the x's that they have in common, the most x's we can take from both of them is 2.
2. Okay.
Yeah. And then to just double check yourself, I always recommend running forward through that multiplication. So 2 times 2 gives us 4. X squared times x gives you x to the third power.
Okay.
2x squared times 1 gives you itself back. So if you run through that multiplication and it's not giving you the original 2 terms back, then you've made some sort of mistake. So there are a lot of different checkpoints where you can see where you've made a mistake or where things are looking a little bit funny before you proceed. And so I always tell my students, and I'm pretty sure I probably told you guys this last week, that you guys just need to check yourselves before you wreck yourselves. Don't be on autopilot and just think like, oh, this is going great. I'm doing fine. I'm flying through this problem. Because then you're going to run into a speed bump that's going to like throw up the question mark and you're going to not know where the mistake happened. So just be very mindful and slowly process this, making sure at every point to check that you're getting those original terms back, right? The same thing over here, the -1 times this gives you the -2x, the -1 times the +1 gives you the -1. Also notice how I'm putting my fingers down and pointing to what I'm multiplying. That's a helpful trick to like physically locate which terms we're dealing with. Because if you try to do them hands-free and all in your head, it's sort of hard to hold those bits of information. So it may seem silly, but putting your finger down and pointing to what you're multiplying out is going to help you focus.
I got confused on the bottom part where you put the GCF, the 2x in the green.
Oh, here.
Yeah, that part. I got confused where you got the 2x squared minus 1. How do we get that?
It's the remaining factors. It's the 2x squared here and the -1 here.
Okay, I see that now.
Yeah, so if we pulled out the GCF from these two terms, you can think about we're pulling them out to the front.
That's like when we do the dividing.
Yeah, it's like you divide them out.
1, or 2x plus 1 and 2x plus 1.
Yeah.
Right? Okay.
So like if you divided them out and multiplied them back in, then you wouldn't have changed the problem. So I know that this is sort of a convoluted way to think about it, but like imagine I had the number 10 and I divided it by 2 and then I multiplied it by 2 again.
That's 10.
Well, yeah, it's 10. So if I divided out 2x plus 1, these guys would disappear, right? Because they would just be 1.
Mm-hmm.
But then if I multiplied it back in and I wrote it here in front, and like I'm multiplying, well, then I should end up with what I started with. So
Okay,
that's sort of what we're doing, although it seems a little bit weirder.
Yeah,
Maybe
no, I see it now. Yeah, I see it
Yeah.
now. Okay, thank you.
Yeah, you got it.
Mhm.
Okay. So now what I want to do is focus the last 30 minutes of class on our third factoring technique. And then maybe we'll have time to get into some special factoring formulas. The third factoring technique is called factoring trinomials. Using the AC method. Okay. So this is a technique that's used specifically on trinomials, meaning that we should be using this only on polynomials that have 3 terms. The AC method gives us a way to change a 3-term polynomial into a 4-term polynomial. And once we've made that conversion of taking a 3-term polynomial to a 4-term polynomial, well, then we can just fall back on factoring by grouping. So we don't have to learn a completely new thing. Okay, we can just fall back on our old ways. So let's take a look at our first example, because I feel like you just learned these by doing. So let's take a look at 4y squared minus 11y plus 6. So we want to take this expression and write it as a product, that is some polynomial times another polynomial. And so the techniques we've learned so far, factoring out the greatest common factor can work on any polynomial, regardless of the number of terms. Factoring by grouping only works on 4-term polynomials, but we're confronted with 3 terms here. So there has to be some sort of method that will allow us to convert this to a 4-term polynomial, so we can just do factoring by grouping. Now, the reason why we call this the AC method is because we're sort of going to label the coefficients of the polynomial, that is, the numbers that are multiplied by each term. We're going to label them as A, B, and C. So we have this first term, and its coefficient is a 4. So we're going to label that as A. The coefficient for the second term is negative 11, so that's going to be our B. And then the final term is a 6, and that's going to be C. So the first thing that we're going to do is multiply A times C. Again, that's why this method gets the name, the AC method. So the first step is to multiply A times C. And in this case, we would have 4 times 6, which gives us 24. We are then going to inspect the factors of 24. So make a factor T chart for whatever number we get when we multiply A times C. So in this case, 24. If we think about all of the numbers, the pairs of numbers that multiply to make 24, we can think of 1 times 24, 2 times 12, 3 times 8, and 4 times 6. 5 doesn't work, and then we're back at 6. Okay. So I like to start with the smaller numbers to see, what we will get, or what we can multiply to make this number up here, this A times C. And then once these numbers get close to each other, that tells you that you're done with the factorization chart. Because like I said, we did 4 times 6, that's 24. 5 doesn't work. And then we could write 6 times 4, but we already have 4 times 6, so we can stop there. Okay. So we multiplied A times C. We looked at all the factors of that number. And now the next step is to choose the factor pair that's going to add or combine somehow to give us the middle term, negative 11. So select the factor pair that combines to make the thing that we labeled as B. In this particular problem, b is equal to negative 11. So if I look at these factor pairs and I add them up, can any of these pairs add to give me something close to negative 11 or just 11?
The 8 and 3.
The 8 and the 3. So I'm going to select those. But 3 plus 8 don't make negative 11. They make positive 11.
Or do you make them both negative?
Yes, and the reason that we're gonna make them both negative is because we need to meet these two conditions. The conditions that we need to meet are that the factor pairs must combine in the following two ways: that they need to multiply to give us 24, and they must add to give us the negative 11. So they multiply to make a times c, and they add to make negative 11. So if I just willy-nilly throw negative signs on these guys, well, that will give me the addition such that negative 3 and negative 8, if I add them together, give me the negative 11. And if I do that, I need to make sure that this other condition isn't messed up somehow. And it turns out that negative 3 times negative 8 does give you your positive 24. So these factors check out. I can go ahead and use negative 3 and negative 8. Does anybody have any questions about that?
No, sir.
Okay. Now another reason why we needed them to both be negative is because I said at the beginning of this process that we need to break up the middle term here, or one of the terms, so that we can get a 4-term problem. So if I go back to my original problem, and I break this negative 11y up into, let me go ahead and put negative 8y minus 3y. If I were to combine like terms here, I would get negative 11y. So it's not really changing the value of this middle term if I break it up into these two pieces. So I can write my whole polynomial out with 4 terms: 4y squared minus 8y minus 3y plus 6, and that's an equivalent polynomial with 4 terms to our original 3-term polynomial. Are you guys okay with that? Do you have any questions?
So far, so good.
Okay. So since we have 4 terms here, we can just jump into factoring by grouping. So these first 2 terms have a factor of 4y in common. And if we multiply this out, if we have a y here and we have a minus 2 there, that gives us our original set of 2 terms. So 4y times y is 4y squared. 4y times negative 2 gives you your negative 8y. And then if I look at the second 2 terms, their common factor is going to be a negative 3, since that first term is negative. And I need to multiply negative 3 times a positive y and a negative 2 in order to get negative 3 times y is negative 3y. Negative 3 times negative 2 is positive 6. Now my factor that's trapped in parentheses is the exact same 2 terms, exact same sign in the middle. So since that's the greatest common factor, I can go ahead and factor that out to the front, y minus 2. And the remaining factors, or the remaining terms here and here, become your other factor. And so you're done. Completely factored. Do you guys want to see one more example before I give you some practice problems?
Yes, please.
Okay.
Yes.
Example 2. Okay. We have 16y to the third power plus 24y squared minus 16y. Can anybody tell me what the first step in factoring this polynomial should be?
Greatest common factor.
Yeah, you should always check to see if there's a greatest common factor. So if I look at all three of these terms, it looks like their GCF, to me, 16, 24, and 16 have a common factor of 8. They also all have a y in common, so 8y is the greatest common factor that I first want to start factoring out. So I'm going to write 8y, and I'm going to open a large set of parentheses, and there should be 3 terms in the parentheses so that I can multiply this 8y and then get my original 3 terms. Those 3 terms should be 2y squared plus 3y minus 2. Does anybody have any questions about that? Awesome. Well, I could factor out the GCF and then I could walk away and say that I did a good job, mission accomplished. But this trinomial here may be factorable. So we can't say that the problem is completed until we've factored every polynomial completely. So we have factored out a GCF, but maybe this trinomial can be factored. And since it's a trinomial with 3 terms, then we're going to try the AC method to see if this guy can be broken down into 2 more polynomials. So I will start by labeling my polynomial here as A is equal to 2, B is equal to 3, and C is equal to -2. I can go over here to the side and say that the first step I need to take is multiply A times C. And in this case, that is 2 times -2. And I get -4. The second step is to make that factor t-chart. So factor -4. And the factors of -4 are simply 1 and 4 and 2 and 2. So we need to select the factors or select the pair that meet the following criteria. That is, they need to multiply to make -4, and they need to add to make B, which is 3. So it looks like 1 and 4 can be combined in some way to give us 3. And since this is a negative number and we need to multiply them to get a negative, that means that only one of them can have a negative sign. So which of these 2 numbers should get the negative sign to meet these 2 conditions?
4.
The 1.
Well, let's think about that for a second, right? The first response I heard is that the 4 should be negative. But if we made the 4 negative, let me use a pencil for this. If we made the 4 negative, -4, and +1, does that add to give us +3?
No.
No. So that means that we've made a poor selection there. We have to go back and see, maybe if we switch the signs, we'll get the correct result. And sure enough, if I have a +4 and a -1, and I add those together, I get my +3. If I multiply those numbers together, I get my -4. So now both of these conditions are met and I can proceed. But you have to make sure that you are not making a mistake when you're trying to meet those conditions. It should naturally occur. So since I have those 2 factor pairs, what I can do is take my middle term here and break it up into 2y squared, but then this one is 3y, and I said I'm going to write that as positive 4y minus 1y, and I'll bring my minus 2 down. Again, these two terms combined, 4y minus 1y, gives you the original 3y. So we really haven't changed the value of that polynomial. We've just simply taken our trinomial and broken it up so that we now have 4 terms, and it's equivalent to the original trinomial. Now we can factor by grouping. So the first 2 terms here have a 2y in common. So I'm going to factor out 2y. That leaves me with a y here and a plus 2 there. The last 2 terms are both negative, so I'm going to factor out some common factor that's negative. 1y and negative 2 don't look like they have anything in common. So if they don't have anything in common, they at least have a 1 in common. So I'm factoring out a negative 1 here. Negative 1 times y will give me my negative 1y, and negative 1 times positive 2 will give me my negative 2. So since this factor and this factor now match, they're a common factor, I can factor that out, y plus 2 times 2y minus 1. And so we factored our trinomial from above. And that should be done, but we need to be very careful because at the very beginning of this problem, we factor out a factor of 8y. So we need to make sure that that is part of our final answer. So our final answer is that we took this polynomial, this trinomial, and we factored it out into 8y times y plus 2 times 2y minus 1. And that is the final factorization. Okay. So I'll give you one of these to practice on your own, just in the interest of time. Try to factor in the next 5 minutes 24x squared plus 42x plus 15. Is anybody stuck or does anybody have any question? Okay, I'm going to jump in. It looks like we have maybe a few people that have finished up this problem. If you were stuck, these take a lot of practice. And so if you feel like we're flying through these really quickly, we are, but we only meet twice a week. And so like you just need to make sure that you're getting in that practice by jumping to the homework. Even if we don't finish the material, you can get into the homework and do some of the problems just so that you're not letting those mental math muscles like fade away, right? We have to continue to go to the gym and develop our muscles if we're training for some sort of sport or competition. The same thing is going to be true for math. Like it's not going to feel any easier until you get into the homework and get that practice. But if we're not doing any reps outside of class, then there's not going to be any development. It's going to continue to feel difficult. I'm not going to go to take a month off from the gym and then go back in there and think that I'm going to bench 250 pounds. It's not going to happen, right? I have to progressively work towards that 250 pound bench press. Same thing, very weird analogy. I'm sorry. Let me go ahead and jump in. If I look at these three terms here in this polynomial, they have a common factor, and it looks like the common factor to me is simply a 3. So I'm going to factor out a 3, and that will leave us with 8x squared. This should be a 14, I think, because 42 is 6 times 7. And if I took a 3 away from the 6, there would be a 2 left over. So 2 times 7 is 14. That's 14x. And then 3 times 5 should be our 15. So I'm now going to sort of label my coefficients here. A is equal to 8. B is equal to 14. C is equal to 5. And maybe in a past math class, you did some sort of factorization process that's similar. Maybe you didn't call it the AC method, where you wrote a big X here, and maybe you wrote A times C here and a B here. It's the same thing. It just looks a little bit different, just the scratch work to the side. A times C is going to be 8 times 5, which is 40. B is 14. So I'm looking for two numbers to put in these spaces so that they multiply to make 40 and add to make 14. So that's got to be 4 and 10. And remember, I said that they need to multiply to make our 40, and they need to add to make our 14. So 4 and 10 satisfy both of these conditions, and that's how I know I can proceed. If I did not correctly satisfy these two conditions, well, then I need to stop and then think of what are other factors of 40. But in any case, that works. I can take this middle term here, break it up into 4x plus 10x, because sure enough, if I combine those like terms, I get my 14x back. So I can rewrite this polynomial as a 4-term problem, 8x squared plus 4x plus 10x plus 5, and then factor by grouping. For the first two terms, it looks like they have a 4x in common. And I need to multiply that out to get the original term. So I need a 2x here, and I need a plus 1 there. Again, that multiplies out to give me the 8x squared and multiplies out to give me the 4x back. For the second two sets of terms, they have a factor of positive 5 in common. So I should be able to multiply this by a 2x and then a plus 1 to get the original terms back. And sure enough, it looks like the common factor that's trapped in the parentheses is the exact same two terms, exact same sign between them. So since that's now the greatest common factor, I can pull that out to the front. And then the 4x plus 5, which were these two factors here and here, become your second factor. So that should be good. But we cannot forget that at the very beginning of this problem, we factored out a 3. And if you do not include the 3 as part of this factorization, well, then you've left a crucial part of the problem out. But in any case, this is now our fully factorized trinomial. Okay. So if you need some more practice with that, if you want some one-on-one sessions with me, just shoot me a message. We can talk about it in office hours. Or if you don't have time for my office hours, or if your schedule doesn't those times don't work for you, there's always Math World Tutoring. I'm going to constantly press you guys to go to Math World to get that extra practice, to get that work, talk it out with a human being, because a lot of times when you're, banging your head against the desk trying to work those homework problems that are really challenging, it's really nice to be able to just talk it out with somebody who can sort of walk you gently through the steps. But the last thing that we need to talk about here before I let you guys go is a special factorization technique. And really, it's a special factoring scenario. So if you have a polynomial where you have a squared minus b squared, you might say to yourself, well, this has two terms. They don't appear to have a GCF or a greatest common factor, right? The variable here is a squared. The second one is here is b squared. So this has a factor of a times a. This one has a factor of b times b. So there's not a common factor here. You might then say, well, this thing isn't factorable. But in this particular case, we call this the difference of squares, because again, the first term is squared and the second term is squared. And in mathematics, difference means that you're subtracting something. So for this scenario, you can use the following formula to factor a difference of squares polynomial. So a squared minus b squared will factorize into a plus b for the first polynomial times a minus b for the second polynomial. So it's the same two terms, but one of them, in one of the parentheses, you'll be adding those two terms. And in the second set, in the second parentheses, you'll be subtracting those two terms. You might ask yourself, why does this work? And in order to answer that question, you have to run through the multiplication. So if I was going to start with this part of the problem and FOIL it out, a plus b times a minus b, then what we would get is a times a, which would give us a squared. Then we would have a times negative b, which would be negative ab. Then we would have b times a, which would be a positive ab. And then b times negative b, which would be our negative b squared. So it looks like we have 4 terms and not the 2 terms that I was talking about here. Well, if I go ahead and finish out this multiplication and combine like terms, you see that we have a negative term here, ab, plus itself. So if I ask you, what is 5 plus negative 5? That would be 0. So when I combine those terms, they cancel out to 0. Even though these are variable terms, if you have something and then you add its opposite or its negative, they cancel out to 0 through addition. So what I can say is that this term here and this term here will cancel out because they're the same term but opposite signs. So I can ignore those or cancel them out and say that this is a squared minus b squared. So here's my challenge for you. And I will start class off with this next time. I want you to factor using the difference of squares formula 25x squared minus 49y squared. and we will look at that next time. Okay, so we ended with a minute to spare. Again, I know that that was a lot. Go to Math World often and early. Make sure that you become very familiar with the tutoring staff there, that you can figure out, which is the tutor that works best for you. Because again, tutoring is not just there for you when you start to fall behind. It is there for you as a constant support resource. So just make sure that if you need even a little bit of practice and you run into those speed bumps in the math homework, that you do that. I'm going to be updating some stuff in Canvas so that you should now be able to complete the R4 homework in MyLab Math. That is available in Module 1. In the next hour or so, I will have the video lecture from today uploaded and the notes that I took uploaded as well so that you can review that. But if you have any other questions later, feel free to shoot me an email in Canvas inbox or send me a message in Remind. If you have any questions right now, you're more than welcome to stay behind. But if you don't, you guys are free to go. I'll see you guys next time.
Thank you. Bye.
See you later, sir.